So we will start with equivalent forces. When a number of forces and moment couples are acting on a body, it is easier to understand their overall effect if they are combined into a single force and moment couple having the same effect. So the purpose of this section is to reduce a set of forces and moment into at one point. Okay? يعني if I have a body subjected to several forces and several moments, I can reduce this system of forces and moment at one point. Then I should represent the total system by one force, one couple. Okay? Now, the idea of equivalent systems is that when I say I have equivalent systems, this means they produce they have same resultant force in overall, and they produce same moment about any point in this. Let us first start by a simple example. If I have here a force F that is pushing an arm BA downward, okay? If I decide to move the force from A to B, can I move it like this, put it at B without changing, without adding anything? They will be equivalent if I put the force here instead of A.
No, doctor.
No. Why? Because look, in this figure, when the force was at A, does it have a moment about A? No. But it has a moment about B. When I displaced the force from A to B, now it will not have a moment about B, but will have a moment about A. So when I displace a force, I cannot do it without adding a couple. Why I should add a couple? Because I should add the couple to create the same effect. For example here, when I move the force from A to B, I should add the moment of the force about B. Why I should do this? Because in this figure, what is the resultant force? F resultant is equal to F that is pushing A. And if I consider, for example, the moment about A, it is 0. And the moment about B is the force F times the distance to B, the perpendicular distance, which is 0.25. And this moment is, the moment of F about B is clockwise. So it is a clockwise moment. Okay. Now, let us try to move the force to B, but still I should have the same characteristics. If I want to have the same characteristics, to be equivalent system, I should add the moment of the force about B. Why? Because when I put the force at B, it cannot produce any moment about B anymore. So to have at the end moment about B equal to Fp times 0.25, I should add a clockwise moment at B that is equal to 25 millimeter or 0.25 meters times F. In this way, I will conserve this condition. And let us make sure now that MA also will be 0 when I do this. If you want to calculate here the moment about A, what will be the moment about A? If I consider the positive direction as positive for moments, and I do sum of moments about A, what do I get? So in this figure, sum of moments about A is equal to, first, I have the couple. The couple, as we said, is a free vector. So if I have a couple moment at B, when I do sum of moment about A, I should include it. So it's plus the moment at B, okay? And now I should add the moment of the force F about A. Let us replace first. The moment at B is 0.25 times Fp. And now for the moment of F about point A, If you look at your figure, from the right-hand rule, you can see that this force is rotating counterclockwise about A. So when I want to add its moment, it's a negative moment. So it's minus the force times the distance. So it's minus Fp times the distance, which is 0.25. So in total, these two will cancel out. This will be equal to 0. So in summary, we say that if we want to displace a force from one point to the other, in order to have equivalent system, I should add the moment of the force about the point. In this way, I will obtain equivalent system. I can never displace a force from one point to one point without adding its moment about the point. Because in this case, if I don't add the couple, I will not have my system's equivalent, since they will not produce same moments about the different points in space. Do you want me to repeat something here? Is it clear? Okay. So now, if I
Doctor,
move, yes,
where do I use that?
I use
When I move the force.
I use it, we will see, we will do a lot of examples. In general, we use this technique when we want to reduce a system of forces to one point. Yani instead of having, for example, if you have a body and like this here, for example, you have several forces acting on the body and you have several couples also. Instead of having all these forces and couple, you say, I want to reduce the system to one force, one couple. So you can select any point on the body or outside the body if you want. You can select any point, let's say O here, and you say that I want to reduce my system to a one force, one couple at O. So what should I do? I should move all forces to O. When I move the forces to O, I should not forget to add their couple about O. Okay? And plus, if I have additional couples on the body, I will add them also to the moment of forces to reduce my system at the end to at O to one force and one couple. Okay, this is called the reduction of system of forces to one point. Okay, so we use it a lot and we'll do examples on this, but just now we should understand the concept that to have equivalent systems, when I displace a force from one point to the other, in order to maintain its effect, I should add the moment of this force about the point. Okay, because when it was far from the point, it was able to produce a moment about it. But when you displace it to the point, it cannot create this moment. So to have the system equivalent, you should add this couple moment on the point. Okay. Now,
Yes,
uh,
doctor.
so this is the condition. Moving a force from point A to O requires creating an additional moment couple. Since this new moment couple is a free vector, it can be applied at any point on the body. So always for the couple, we say it's free vector, so I can put it everywhere. And I can put it in particular on the point I move to, okay? Because as I told you, the couple, when you do sum of moment about O, for example, all couples will be included in your summation because couples are three vector. Yani a couple, you can displace it without changing anything. While a force, you cannot displace it without adding its moment about the point. Okay, this is the difference. The force, when displaced, should we should add its moment about the point. However, if I have couples out on any point of the body, I can move them without changing anything because we have seen together that the couple is a free vector and it's producing the same moment about any point in the space. Okay. So here, this is an example, okay? How to reduce several forces and several couples onto one force, one couple at one point. So consider here this rigid body, for example, okay? This rigid body is subjected to forces F1, F2, and couples, and it's subjected to couples, okay, to a couple MC. So now, if I want to reduce my system to O, what should I do? For the couple MC, I can move it to O without changing anything. So I just place it at O. This is M of C. Okay? Now, when I want to move F1 to O, when I want to place it at O, I should add its moment about O. So I should add M1 equal, what is the moment of F1 about O? It's R1 vectorial F1. So this represents the moment of F1 about. And when I want to displace F2 to O, also I should add its moment about O. So I put F2 at O, but also I add its moment about O, which is calculated as R2 vectorial F2. And once I do this step, now the resultant force will be sum of forces. So in this example, the resultant force is F1 plus F2, while the resultant moment will be equal to summation of moment of forces. This is what we mean by summation moment about O, which is our M1 and M2, R1 vectorial F1 and R2 vectorial F2, plus what should we add to it? The moment of couple. So here I only have one couple, so I add plus MC. So the general rule is the following. When I want to reduce to one point, the resultant force is the summation of all forces acting on the body, and the resulting couple is summation of couples acting on the body plus summation of moment of forces about the point. Now, in case my force system is in XY plane, in this case, all moments will be along Z, okay? So I can write it in this way. I can say that in the force, I have two components. The resultant along X will be equal to sum of X. The resultant along Y will be equal to summation of Fy. While for the resulting moment, it is along, since it is along Z, I can do an algebraic addition. So I consider, for example, let's say the counterclockwise as positive. I add all couple moments to moment of forces. And of course, the counterclockwise, I count them as positive, and the clockwise, I count them as negative to respect the convention I select. Yeah, we will see this in example, so it will be more clear. For example here, the street light shown below is supported by cable AC. The total weight of the structure is 1,600 Newton acting at point G, and the tension in the cable is 3,600 Newton. The 200 Newton horizontal force represents the effect of the wind. Replace the force system by an equivalent force and couple moment acting at point B. So here we have a structure, okay? This structure, as you can see, is subjected to several forces. I have first, it is attached to a cable, applying on it a force of 3,600 Newton, and the angle of this force is given here to be 45 degrees. It is subjected also to the action of the wind through a horizontal force of 200 Newton, acting at 4 meters from point B. So this distance is given to be 4 meters. And also you have the weight of the structure. So the weight of the structure acting at its center of gravity, which is equal to 1,600 Newton. And we have that here the height is given. Okay. the total height of my structure is 5.5, and I have all distances needed. So I have here the distance from G to A is 1.3. Now, the objective of this problem is to reduce my system to one point. I want to reduce all forces acting on my system at point B. Okay, so what is the technique? When I move any force from one point to the other, I should add its moment about the point. Okay, so first let us start with the resultant force. If I want to find F resultant at B, the resultant force will be the same whatever is the point of reduction, because how I calculate the resultant force, it's summation of forces. Now, what will be different if I, from point to point, and if I reduce at A, for example, instead of B, I will have same resultant force, but different moment, different resulting moment, okay? So here, since I selected B, when I do displacement of forces to B, I should add their moments above B. So first, for the resultant force, okay, since I have here a 2D problem, I can decompose my resultant into X and Y, okay? Because I know that here the F resultant vector is the summation of three forces, F1 vector plus F2 vector plus F3 vector. So now I can decompose this vectorial relation into two components. The first one is the resultant along X. For the resultant along X, I have first for the cable force, okay? The cable force is directed downward with an angle of 45 degrees. So I can decompose it into two components. I will take X positive like this and Y positive upward. So I can see here that this force has a negative projection along X and negative projection along Y. And since the angle is 45, so I can do to project on X, I can do cosine 45. So I have that FRX is minus 3,600 cosine 45. And along, so this is the component of the first force along X. The second force is the wind action. As you can see, the wind action is the one here. It is positive and it's horizontal, so I don't need to project. It's along X, so it's plus 200. While for the weight, it's vertical, so no component along X. So this is FRX. Now, for FRY, first, I project the cable force, so it's minus 3,600 sine 45. For the wind action, it's horizontal, no component along Y. And for the weight, it's vertical downward, so it's minus 1,600. Now, I obtained the resultant force. Okay, so now if I want to get, once I have FRX, FRY, okay, I can simply find the magnitude by doing the radical, and I can find the angle by taking the tangent minus 1 of absolute value of FRY over FRX. Okay, now we are done with the resultant force. The next step is I want to find the resulting moment at B. Okay, so now to find M resultant at B, this is equivalent to find the total moment about B. Okay, because when I displace a force to B, I should add its moment about B. In this problem, we don't have couples. Okay, so if we have couples, we should add them to the summation of moments. So the resulting moment about B will be equal to the moment of F1 about B plus the moment of F2 about B plus the moment of F3 about. And also here I should select a, positive direction. So I can take, for example, the counterclockwise as positive. And now I will start by the first force, this tension here. To find the moment of the tension about B, I have several ways. The first way is to say, since this force is decomposed into X and Y, I will consider that the moment of this force is the moment of the X component about B plus the moment of the Y component. But as you can see in your figure, the Y component of this force is passing by B, so it will not produce any moment about B. So the only component of the force that produces moment about B is the horizontal component. Now, it is producing a clockwise or counterclockwise moment about B. Look, try to do your right hand rule. Or even you can do it like this with your pen. It's rotating, it's tending to rotating with a circle like this. So I'm moving in the counterclockwise direction. So it's a positive moment, okay? And in magnitude, it's equal to the component, and here it's the magnitude of fx is 3600 cosine 45. I should multiply it by what? The perpendicular distance from B to the line of action of the force. The perpendicular distance is equal to what? To 5.5. So the first moment of the first force is plus 3600 cosine 45 times 5.5. Okay, so this is the moment of the first force. Now, just before continuing with other forces, you have another method to find the moment of this force about B. What you can do, you can say, I know the line of action of the force. I find the perpendicular from B to this line of action. So if I draw the projection, I say that the moment is the distance times the force. And how to find the distance here? You can calculate it.
45 times cosine
Exactly.
45.
Yes, you can do in this triangle here, in this big triangle. You can say that I know that here, this angle here is, this angle is 45, okay? And this is the hypotenuse here, 5.5. So this distance perpendicular is 5.5 cosine 45 or sine 45, okay? Then once I find the distance, I multiply it by 3600. So I will get back to the same result, which is 3600 times the distance, which is 5.5 cosine or sine 45. Here it's the same. Okay? Now, let's move.
Doctor,
Yes.
so whenever I calculate the sum of moments, I don't look if it's on the positive side or negative side. يعني the components, if they are positive or negative, I only look if
Yes,
it's clockwise.
exactly.
Okay.
Because
Thank you.
look, if a negative component of a force can create a positive or negative moment. Because look, if this component was here, was down, it will create a negative moment. For the sign of the moment, you don't look at the sign of the component, you look at the direction of rotation produced by this component. Okay? So here,
Yes, doctor. Thank you.
even if it's a negative x component, it's producing a counterclockwise moment. So it's a positive moment. Okay? Now, to continue with the other forces, we have the action of the wind. Okay? The action of the wind, which is equal to 200 Newton in magnitude, is at a distance of, perpendicular distance from B of 4 meters. And now concerning the direction, it is turning how? It is turning like this, about B, clockwise. So it's minus. So it's minus 200 times 4. And finally, for the weight, okay, for the weight of my structure, first, it's rotating in the clockwise direction about B, so it's a negative moment, and I should multiply by the perpendicular distance. So if I take the line of action of the weight and I draw the perpendicular from B towards this line of action, what is the distance? This is the perpendicular distance. It's equal to 1.3 meters. So I do minus 1,600 times 1.3. In this way, I get the resulting moment about B. So what I did now, I reduced the system of forces acting on my structure to one force, one couple at one point. Okay, this is what we say. This is what we call reduction of force system, force and moment system. Okay, now I will just add something. In case I have a couple on the structure, for example, here, if they told me I have a couple here equal to, let's say, 100 Newton meter, what should I do? When I do sum of moments about B, I say I should add this couple. Since this couple is clockwise, so it's a negative couple, so I add to my summation of moment of forces, I add minus 100. Okay? Any question on this? So let us see together the details of this.
Doctor,
Yes?
I didn't understand the last thing that we did just now by adding minus 100.
Okay. Look, we said that a structure can be subjected to forces and couples. Okay? In the example they gave, they just consider force action on a structure. But also you can have a couple, a moment. Okay? A moment. If you have a moment acting on your structure, when you do sum of moment about any point, you should include the moment vector, because the moment is a free vector. So if you apply it at, for example, A, it will also have the same effect on B. Okay? This is why when you have a couple acting on your structure, when you do sum of moment about any point, you should include it in the summation of moments. Okay? So you look at your couple, you have its magnitude, it's 100, and you look at its direction. Since it is a clockwise moment, then it will produce a negative moment about B. So it's minus the couple, which is minus 100. Okay?
Oh, okay, thank you.
So now, they did the same step we did together. First, they found FRX, FRY. Once you determine these two, okay, you can find the magnitude of your force. And as you can see here, since the resultant in X and the resultant in Y are negative, this means that your force is in the third quadrant. So now I can draw a small scheme showing my force, and to define it completely, I can find the angle with the horizontal. So here I say I want to find this angle. It's tangent minus 1 of absolute value of Ry over Frx. I get that theta is equal to 60.5 degrees. And for my moment, when I did my calculation, here, as you can see, they said we should add sum of couples to sum of moment of forces. But since we don't have couples in this problem, it is 0. Okay? Plus the moment of forces. This is what we did together. We have done together. And now, once we calculate the resulting moment, we get a positive result. This means that in total, the resulting moment is in the counterclockwise direction. So as you can see here, I reduced the system of my forces to one force, one couple at point B. Okay? Any question on this problem before we start something else? Okay. Now, until now, what we did is we reduced the system of forces to one force, one moment at one point. Okay? Now, sometimes they can ask us to reduce a system to a single force. If we want to just have a single force acting on our system, we should, if you want, try to find the location of application of the force in a way to not need a couple with it. What do I mean by this? Let us take an example. You have this body. This body is subjected to several forces and several couples. So the first step you do is to reduce the system of forces to one point. So for example, here they selected O. They said we want to reduce the system of all forces and all couples acting on the rigid body. We want to reduce it to point O. So they do the same procedure we did in the previous example. To calculate the resultant force, they will add all forces acting on the system. So here, as you can see, for example, you have on the body, you have, let's say, F1. You should add to it F2 plus F3 plus F4. In this way, you get the resultant force. Okay, so let's say this is the resultant force. And now the next step is to find the resulting moment. To find the resulting moment about O, first I add moment of all forces about O. So I do R1 vectorial F1 plus R2 vectorial F2 plus R3 vectorial F3 plus R4 vectorial F4. And I don't forget to add what? The moment vectors, okay, the couples. So I have here two couples. I add them to the moment of forces. And I end up with one force at O and one moment at O. So now I reduced my system to one point with one force and one couple. Sometimes we are able to reduce the whole system to one equivalent force without the need of a couple. How? In this case, when you reduced at O, okay, you can get in a particular case, you can get the moment and the force perpendicular. Okay, this is a typical case in 2D. Why? Because look, when you work in a 2D problem, okay, in a 2D problem, for example, all forces will be in XY plane. And then the resultant force will be in XY, while the moment will be along Z. So it will be perpendicular to the force, okay? So in many cases, when you reduce your system, you reduce it to one force and one moment vector that are perpendicular. And when the moment and force are perpendicular, this means that you can end up with a single force. Why? Because you know that a force can produce a moment only about an axis that is perpendicular to it. A force can never produce a moment about an axis that is parallel to it. So here, let us see together, for example, if I displace the force backward, if I displace it backward, can I select a certain distance, D, any way to produce the couple moment about O, yes or no? Look, if I displace the force along this direction, it will produce a moment about this axis, yes or not? Yes, because look, if I put my force here, for example, okay, what will be its moment about this axis? If you want to calculate its moment about this axis, its moment will be equal to the perpendicular distance between them times F, okay? So when I displace my force in this direction, it will create a moment about it. So I can displace it in a way, I can just select a corresponding distance in a way to produce the same resulting moment about O. Once I reach this distance, then the single force will be able to represent my system because it can produce the same effect about O. Since we said, what is the condition for equivalent system? The condition for equivalent systems is to have same resultant force and same resulting moment. So try to compare these two figures. In this figure, I reduced at O. What do I have? I have a resulting force Fr, and I have a certain resulting moment at O. Okay? Now, in this figure here, what I did is that I displaced my force backward. And who can tell me why we displace it backward and not towards the right, if you want?
Because if we were to do it to the right, the moment would be backwards.
Because if you do the right-hand rule, okay, you know that your purpose is to produce the same resulting moment about O. If you move it backward and you do the right-hand rule, your sum will point. Try to do the right-hand rule here. When you do your right-hand rule, your sum will point in the direction of M resultant about O. But if you move it in the opposite direction, what will happen is, so if you move it like this to the front, then your sum will be directed in the opposite direction of MRO. So I cannot create the same moment about O if I displace it like this. So I should displace it backward in order to ensure the same sense of the moment. And the corresponding distance I should select, I should move it a certain distance in a way to create the same moment about O. So the condition is that my force Fr times D should be equal to the resulting moment about O. This will ensure the condition of equivalent system. So in general, what can they ask you? They can ask you, what should be the distance D I should displace my force F in order to reduce my system to a single force? Because when I displace this distance, just by having the single force, I can create the same effect about O, since my resultant will be Fr, and my moment about O will be Fr times D equals to MRO. So I say, so what should be D to ensure equivalent system? D should be equal to the resulting moment about O over the resulting force. In this way, I was able to reduce my system of forces and moment to only one single force. Okay? Yeah, we will repeat. I will repeat the concept if you want,
Yes.
But just because the session is over, so I will open a new one. Okay?
Yes, doctor. Thank you.